Okay, this is our Chapter 6 review. And we've done a lot in Chapter 6, but at least that's all been related, so maybe that's helpful. Number 1 and number 2 is just a reminder of how to write a rational exponent as a root and vice versa. So number 1, they want us to write the rational, the exponential expression in radical form. So the 3 is like, doesn't have an exponent on it, so I know there's a 3 in the front. It's the x to the 3/8 power that I need to worry about. Remember, the bottom of the fraction is your index, or in this case, the 8th root of. And then the numerator stays an exponent, so x to the 3rd. Number 2 is just that backwards. We want to write the radical expression using rational exponents. So that's going to be 4 to the negative 10 over 7 power. And you can leave it like that. I mean, technically it's a fraction, but that's it. So that's the solution to those two. Those are pretty straightforward. Number 3, we're solving the equation. Remember when we did this, we had to use those exponent properties. And here I can see I have 2 3's, but with the different exponents. So now I'm going to want to add those together. So the first thing I need to do is I need to add x over 5 plus x over 4. My common denominator is going to be a 20, right? I don't know why I put it to the side like that. Boop, boop. If I multiply this times 4, I have to do this times 4. If I multiply this times 5, I have to do this times 5. So it just becomes 4x plus 5x, or 9x over 20. So what that means is, switching colors here, is this is going to, when I multiply them together, turn into 3, and then the exponent will be 9x over 20, and then of course the other side is 3 to the 2nd power. So that's the hard part, is getting your fractions or rational exponents added properly, and I don't feel like that's too bad. The easy part, in my opinion, is the rest of it. I can see that here my 3's are the same, right? That's what you want. You want your two bases the same. And so I can now officially ignore those and just set my two exponents equal to each other. So I get 9x over 20 has to equal 2. So I'm just going to multiply by the reciprocal of that, which would be 20 over 9 times 20 over 9. Now if you want to leave that as 40 over 9, I'm more than okay with that. As a matter of fact, it would probably be good practice to leave it that way, because that's usually what we deal with in upper math. If you want to reduce it, find the decimal, fine, but like 40 over 9, perfectly acceptable answer since it is a reduced improper fraction. Number 4, I do ask you to sketch something and then tell me what the asymptote is. So I'm going to come down to my graph paper for that. So this one is going to get pretty large, as we're going to see, because it is y equals, or f of x equals 5 to the x power. Now remember, I would suggest sticking with using -2, -1, 0, 1, and 2. If you want to use other numbers, great. That's what I'm going to stick to. So I need to figure out what 5 to the -2nd power is, and I cannot do that one in my head, so let me use my calculator really quickly. It's 0.04. Well, that's really not nice. 0.04. Then 5 to the -1st, I can do that one in my head. That one's just going to be 0.2. Of course, anything to the 0 power is 1, 5 to the 1st is 5, and then 5 squared is 25. So that's what I meant by I'm going to have quite a graph here, because obviously my x values aren't so bad, right? I'm just counting from -2 to +2. It's my y values that are going to be not so fun. And you're going to have a whole sheet of graph paper for this, so I mean, you can count by whatever you want to. Here, I'm going to stick to my counting by ones because it's not so bad. And then I am going to count by 5s here. 5, 10, 15, 20, 25. I want to make sure I label that. And obviously I'm going to have to estimate on all of these except for like 2. -2 and 0.04 is going to be like way down here. And -1 and 0.2 is not going to be much taller, especially since I'm counting by 5s. That would be really hard to see. 0 and 1 is actually going to be like right here. Like I can't really, I'm going to have to estimate that too since I'm counting by fives. 1 and 5 is here, and then 2 and 25 would be here. Okay, so we know that it's going to have that shape, and y'all, I cannot draw these on this iPad, so just kind of bear with me here. So we know that it curves up really fast, and that's our exponential graph. So I do ask you to sketch that. And of course, that would make my asymptote, as is with all of the functions that I'm not adding and subtracting whenever they're exponential. The asymptote would be the x-axis. Number 5, I give you a table and I ask you to decide if it's linear or exponential. I can see here that it looks like I'm multiplying by 4, I think. Let's check. Yep, that's times 4. Yep. I'm multiplying by 4 each time, right? So the answer is that it would be an exponential function. And it's because you are multiplying. I can spell, there we go, by 4. 4 would be my common ratio, whatever you want to think about that as. Number 6 and number 7. These are my exponential growth and decay problems. So we need to remember we have a starting amount, right? So in this case, that would be the value of the boat. And then somehow it's going to be decreasing or increasing. For number 6, they're telling me that it's decreasing by 12%. Now remember, decreasing, I'm going to have to do some subtraction. So 12%, first of all, is 0.12. And I'm going to do 1 minus 0.12. I believe that's 0.88. Okay, so that's going to be my B, right? And then 5 years, of course, will be my time. So in my calculator, let me scroll down. This is a lot of work, so I'm going to do number 6 down here. Excuse me. I know I'm finding the value of the function at 5 because it says, 5 years. Again, the initial value of the boat was $8,350. It has a decay rate of 80.88. And then again, the time is 5. So I'm just going to type that in my calculator. Times 0.88 to the 5th power. So the value of the boat after 5 years would be $4,406.56. That's number 6. So number 7 is very similar, except for this one, you're growing. So for the rate on this one, and I'll do it up here, again, that's 0.02, but I know I'm going to add 1 since it's a growth problem. So that would be 1.02 that I'm going to be using for my B. This is obviously a deer population problem. So this time was 4 years. So I'm finding the value of the function at 4 years. The initial population was 1,500 deer. That seems small. And then 1.02 was my growth rate. And then again, 4 years is where I want to check my population. So 1,500 times 1.02 to the 4th power is, and I'm going to round this one to a whole number because we are talking about animals. So it would be approximately 1,624 deer. That's number 7. Okay, so while I'm here, and you can see it on your paper, number 8, this is the one that I need that formula for, where we did the investment. Okay, so this is the formula that we have for number 8. Again, the rate they give me is 7%, so that's going to be 0.07. It's compounded monthly, and I know there are 12 months in a year. So I'm going to do 1,400. That's the principal amount, the amount that's being invested. 1 plus the rate, again, is 0.07. Compounded monthly, so that would be 12 months in a year, and then 12 again. And then the number of years they want me to check is 22 years. That's a lot. All right, so let's type this in my calculator. 1,400 times 1 plus 0.07 divided by 12. Make sure I'm using my parentheses and my exponents carefully. 12 times 22 as my exponent And at the end of that 22 years, I would have $6,501.27. That's number 8. So you need that formula. Number 9. This one's easy. Number 9, is this sequence geometric? In other words, are you multiplying by the same thing or not? And we can see here that it is not, right? Because here you're multiplying by 2, but here you're multiplying by 4. Here you're not multiplying by anything. It looks like you're adding something. So definitely no consistency here, so it is not geometric. If it was geometric, it would look a lot more like that table that we did back up on number 5, right? That's a geometric sequence, 16, 64, 256, where you're multiplying the same thing. And if it was geometric, like up here, the common ratio was 4, so that's what that means. All right, the recursive formula. I'm going to ask you for the recursive formula and the explicit formula for number 10. So I'm going to go ahead and write both of those down. So the recursive formula, remember, is A sub n equals, what am I multiplying by? So I can see here I'm going from -2 to 8, and then from 8 to -32, so I'm multiplying times a -4. So it would be -4 times A sub n minus 1, but you also have to tell me that the first term is -2. So that is the recursive formula. The explicit formula, let's do that in a different color. It's not much more difficult. I feel like this one's easier. So the explicit formula, A sub n, remember it's your first term, which is -2, times what you're multiplying by, in this case -4, to the n minus 1 power. So that's the explicit formula for number 10. Okay, so number 11, I'm not going to ask you to graph that one. What I'm going to ask you to do is to tell me about the graph. Where is the asymptote at? Did it move left or right? Did it move up or down? So this one, since I'm adding outside of the function, I know that this one is moving up 4, which would also make the asymptote move up 4. And so the asymptote would actually be the line y equals 4. Right, it's whenever you're adding to the exponent is whenever it moves left and right. So you wouldn't move the asymptote there, and it would stay the x-axis. So again, please be able to tell me about that. Number 12, it says, suppose the transformation of the parent function, and I know you can see it because I wrote all over it, 10 to the x, is given as a times 10 to the x. Right, so a is going to be a number, but they're saying, hey, it's a negative number. So what's going to happen to the range of the function? Well, remember the range of the function, like normally when I graph these, just like we did that one just a second ago, right? It was up here. The range of the function was all positive. Now we talked about how if you put a negative in front, then what's going to happen to that graph is it's going to flip upside down like that. So the effect that it has on the range is that the range is now going to be less than 0, or you can say that it's negative. It's going to be a negative range. Now, remember how we talked about if the negative is instead on the x, we did that in Desmos, it wouldn't change the range, right? That's the one that it just flipped it over and it looked like this. So the range was still positive, it just flipped it over the y-axis. So be mindful of where it's saying where the negative is at.